Okay, so welcome back. In today's video, we want to talk about proving multiple variable limits. Last video we talked about how we could um, disprove limits and how that was often easier to do than proving them. So as I said in the last video, in a single variable case, right? I have a number line and I want to prove a limit at this point. If I prove that the limit from this side and the limit from this side are the same, then the limit is proven. However, now instead of dealing with that sort of thing, we're dealing with a plane, the xy plane. So if we want to prove a limit here, then we need to prove that it gets to the same limit from this point, this point, this point, this point, this point, all the way around. So we need to be a lot more comprehensive with our proofs. And even finding just one of these infinite number of different radial lines that we could have, or radial parabolas or whatnot, um, that disproves the limit. So proving a limit means you need to go to the precise definition, which is the epsilon delta definition. So it gets quite technical, and this is why we don't use multivariable limits as frequently as we use the single variable limits. Okay, so let's try to prove one, but first let's refresh our epsilon delta definition. If for every epsilon greater than 0, there is a corresponding delta greater than 0, so that if x comma y is in the domain D, and 0 is less than the square root of x minus a squared plus y minus b squared is less than delta, then there exists some epsilon such that f of x minus y, f of x of y minus L is less than epsilon. Let's try an example. Now this is going to be fairly technical. I'll try to walk you through this proof, but it's fairly difficult. Anyways, I would like us to determine the value of the limit as xy approaches 0, 0 of 3x squared y over x squared plus y squared. Now, before you even go to the epsilon delta case, what you want to do is make sure you can't disprove the limit with any easy shortcuts. So let's say you're at the point where you've tried going along the x-axis, you've tried going along the y-axis, and you've tried going along all the radial lines and all the radial parabolas, and you've determined that this value equals 0, you've determined that it equals 0 for all of those values, then you can say, okay, maybe the limit does exist. I'll move on to an epsilon delta proof to prove that the limit exists if it does exist. So what we're going to do is we are going to say if 0 is less than x squared plus y squared, because we're at 0, 0 here, so we don't have any x minus a squared plus y minus b, we just have x minus 0 squared plus y minus 0 squared, is less than delta, then the function, the magnitude of the function minus the value of the limit that we think it is, so 3x squared y over x squared plus y squared minus 0, which is what we think the limit is, because that's what we would have found from all of our guesses with the x-axis, y-axis paths, is less than epsilon. So now we can move on to the proof. So but x squared is less than x squared plus y squared, since y squared is greater than 0. Thus, x squared over x squared plus y squared is less than or equal to 1. And this means that we can say that 3x squared times the absolute value of y, because y is the only thing that could be negative, over x squared plus y squared is less than or equal to 3y. Now we can write 3y, 3 times the absolute value of y is equal to 3 times the square root of y squared. So we can write that that's less than or equal to 3 times the square root of x squared plus y squared. So now we're prepared to make our choice for delta, because this would be our given epsilon value, likely. So we will choose delta to be epsilon over 3. So thus, 3 times x squared y over x squared plus y squared minus 0 is less than or equal to 3 times the square root of x squared plus y squared, which is less than or equal to 3 delta, which is equal to epsilon. Okay, so we've made the proof that this limit does exist and it is 0. So as you can tell, these proofs revolve mainly along the on the idea of the function. You need to use the properties of the function in order to take advantage of your epsilon delta proof. And we can see now that this limit is going to be 0. And we can look at a graph here. As you can see, we've got a little undefined space right here in the middle. But as you can see, it approaches 0 from pretty much everywhere. Down from there, it approaches 0. It approaches 0 from there, and all the way up here. And then over here, it probably comes down and back down into the blackboard. And up here, we're still approaching 0. So we're approaching 0 from everywhere. That means that the limit exists. Okay, in the next video, I want to cover really briefly continuity, and then we'll introduce partial derivatives. Thanks for watching. See you next time.